Good morning. I'm Bengi on the Cloud Warfare presenting stream communication. That is our outline. We have in this stream communication, we're doing some introduction, then support for continuous media data stream and quality of services, the stream synchronization, how do they synchronize it, and we have the sub menus there. We'll look at them in details. First, let's look at what is even communication self. When we are talking about communication, we are talking about how information is being exchanged, but here we are talking about something that is concerned with computer-based something. The information being exchanged from one device to another. And this information can be time dependent or non-time dependent, and some whether is the speed of communication, as in the data which we communicate, is too slow or too fast, may not affect it. And this is, like we say here, a system may perform too slow or too fast. Time has no effect on the correctness known as time. That's what we're trying to show here, is that time is time independent or otherwise is time dependent. When there is a correctness, the system that may perform too slow or too fast, time has no effect on correctness known as time independent. It's independent of what time is. And our interest in this particular thing, we are considering a distributed system which offers time dependent information system such as audio and video. Like for example, the time independent the time independent system, like if you are transferring a movie from one system to another, you know, like now you are transferring a file. That file you are transferring bit by bit. When you start the thing or when it ends does not affect the accuracy of that system. But this time dependent. For example, if you are watching a video online, you are streaming a video, then what you are transferring at that point, you are transferring and watching, then it needs to be coming in a bit that could be able to play. Like for example, your YouTube videos, when you are streaming, the network is slow and you'll be having trouble with it. But for example, if you are downloading the video, whether the network is slow or fast, when the video is completed, it's completed. There is no error due to the time something. When it's finished and it's complete. But here we are looking at time dependence information system, the one that depends on time. That is a streaming stuff. Now let's move to the next slide. We're talking about support for continuous stream. Now, since it says support for continuous or time dependent information is often formulated as support for continuous media. An important type of this medium is how the information is being represented. We're talking about representation. Now, a medium is referred to as the way that we convey the information. Like here in my slide, say they refer to medium refers to the means by which information is being conveyed. Is it a continuous representation or a discrete representation? In a continuous, the relation between different data items are fundamental to the correctness and interpretation of that particular video. But discrete, which say that is characterized by fact that the temporal relation between the data item is not fundamental to the correctness. For example, transferring a file, you might transfer a text file to a particular point. You leave it. Maybe if it opens, it will open to that point. That is where they read. You read the top to down, the correctness will be there. But when you are talking about continuous, as the data is coming in continuous form, you need that, okay, the relation between the audio and the video should be correct. We are playing a video, that is a continuous data. You are using it continuously there. Or maybe it's they use, like I give it an example down there of discrete of, let me go back, of time dependent system of video, YouTube video. This one is continuous. That's the interpretation between the audio part. Maybe if we are talking about video now, the audio part and the motion is also there, the picture or the picture motion. Okay, now let's move to data stream. To capture exchange of time-dependent system, distributed system generally provides support for what data stream. Data stream can apply for both discrete and continuous data. What is data stream? So I say it's a sequence of data unit, and a string can be applied for continuous, discrete and continuous, as been stated before. And to capture the timing aspect of this is often made between the different transmission mode. If we are trying to, okay, let us look at the timing of these things. We look at them in how did they transmitted? How are they transmitted? The modes at which they are transmitted. Like they give you an example, there are TCI connection. We use data stream, and playing an audio is a continuous data stream. What I've tried to explain in the previous slide. Look at it. A TCI connection is an example of byte-oriented discrete data stream, and a playing an audio requires setting a continuous data stream. Now you're playing an audio even maybe from a remote media or even on your system. It requires you to set a continuous data stream for that. That will be continuously updating with time respect. Now, this transmission mode, we have three of them: asynchronous, synchronous, and isochronous. Asynchronous, this is the basic one that is used. We do not have anything like, okay, there is a timing stuff. There's no timing stuff. When the data start, when the data end is correct. And one thing we should know here is that there is a resend. If we lost a packet, we are going to what? Resend the data. The required resend of data lost. And example, we have a discrete data stream. Example, we have a file. You are sending a file. When a data packet is lost, you have to resend it. Okay, I said this. Let me read from the stream. It's a made of data items in a stream are transmitted one after the other, but there is no further timing constraint. There's no timing constraint. Now synchronous. With the fact about this is that synchronous have timing constraint. That is what makes this one different from the asynchronous. Have timing constraint, or any other thing is correct. That's why the example here is audio and video, playing a YouTube, a video, online video like that, playing a continuous data like that, maybe from a online stream, or even from your system. So the only thing that we don't observe that in from our system is that our system has the capacity of transmitting that frequently. But if you are working on if your system is congested, sometimes even the data stream there will be pausing out, giving us a pause that, oh, there is something wrong. They need to get the data before they can play. Okay. Now asynchronous. This is the last one. The last look at synchronous mode is data transfer between method in a continuous stream of data signal is accompanied by timing signal. Timing signal to ensure that the transmitter and the receiver are in step. That is when the receiver sends, the other one should receive. They are in step. No one is leaving the other. Okay. Asynchronous is transmission mode in necessary to it's a transmission mode. It's necessary that the data units are transferred one on time and the combination of the first two. It does not require resend of packet lost. Example, we have video and audio calls. For example, if you are making an audio call like that, if you lost a packet is lost, it will show from the other person. But if you send it continuously, the packet will be losing. It will be as if you be speaking in, you say something in at time 01, and they will give you that thing at time 06. If the packet at time 01 lost, send the one at time 02. Let us continue. The person will observe the deviation, will still resent by your way of talking, by the two of you. Now let's move to what streams are. Streams are continuous data stream using asynchronous transmission mode. Basically, what we are considering here is asynchronous mode in this stream, in this our chapter. We're considering this particular one, asynchronous. Now, let's go to stream. Stream are considered as a continuous data stream using asynchronous transmission, which we refer simply as stream. It says stream concentrate only a single sequence of data, and stream can be complex or simplex. A simplex one is that it contains only a single sequence of data, and then the complex one may have two or more simplex streams in between them needed to be transferred, and maybe there are time independent stuff. Okay, now let's move to quality of service. How is this thing, how are we trying to ensure that the requirement of this system are met? Let's take the first quality of service here is that the required bit rate at the data should be transported. The required bit rate that to be transmitted should not carry that there will be no error, there will be no time lapses or anything latency like that. The required bit at which data, the required bit rate, that is the sending rate at which data should be transported, the maximum delay until session has been set up, the amount of buffer before the thing can start sending the data, the maximum end-to-end delay, okay, should not send too far so that the other one will be having data that cannot be able to manage. Should send a bit by bit such that the other one should be able to make it. If you that is maximum end-to-end delay. You know you have the capability of sending 2 MB at once, but send 1 MB. Maybe the other system have just a RAM of um, a RAM of 2 MB. If you send it too much, you cannot receive it, and you have problem congestion at that system in the RAM. Then you need to send it in a way that you can receive and be able to manage. The maximum delay invariance, that is the jitter. When you're talking about a jitter, that is a variation in the packet. The maximum delay variance, that is the jitter. When we're talking about how the delays are making, we look at that in the next slide. The maximum round trip delay, so much of them. We have to ensure all these things. Now, given that underlying system offered best of effort service delivery, that is best of effort when you are trying to use buffer and jitter. Jitter is a delay invariance packet arrival. The delay, that the variation in packet arrival, maybe the other one with 2 seconds, the other first packet will arrive 2 seconds, we delay for 2 seconds to arrive, the other one 3, 4, 5, kind of the delay variance. Our underlying system, the system is being made in such a way that, okay, no matter what, should try and deliver the particular information. Now let us still talking about enforcing quality of service. Well, assuming that a packet of a certain variance transmitted over a network receives store assuming with a certain variance when it transmitted over a network, the receiver simply stored them in a buffer for a maximum amount of time. This will allow the receiver to pass packet to the application at regular rate, knowing that there is always enough packet entering the buffer to be played at that rate. What I explained that first, the heading here we have using buffer to resist jitter. That means you should be able to receive to a certain amount that can be able to start playing, but no matter kind of packet, no matter kind of jitter, you'll be able to manage your playing. You should not start a first sending such that maybe if the other one will be taking 3 seconds, we have to wait for it. Look at it here. Here is the buffer. Look at the buffer time, buffer in time. Okay, packet. The source we have 1, 2, 3. Send at to 8. When we send the packet, okay, this is the packet depart source. Packet arrive at buffer. Packet remove from buffer. Good. This is when it started playing at 10 seconds. When you're loading a video, sometimes you wait to receive or to the buffer before you start playing. It will play continuously, but here we have a gap. Yeah, a gap because this very one arrived at this point. Look at 2.7. There is a jitter. This is our jitter, the variation in the delay. Had it been that this thing is the same, would have been cool. because we know when to start receiving or how much our buffer could be before it could play continuously, but there's a variation. Then we observe a gap here. Look at the explanation from that graph that I've already said. A packet that took 11 seconds to receive. At the time, the buffer have to be completely empty, and then there is a result at the gap. The solution is to increase the buffer size. Drawback is that the delay at which the receiver application will start playing the data contained in the packet increase as well. Already mentioned that up there. Okay. Now let us say that we are now dealing with an underlying burst of effort from that period or something that sending we don't know. It also means that the packet may be lost. That one we didn't even talk about the packet lost. We just knew that everything that has the best efforts. We consider that is the best case. Every packet is sent, but only thing is that there is a delay in it. Okay, requesting resend or transmission of data, that is what we are not going to do because we are dealing with an asynchronous transmission mode. We say resending is not allowed. To compensate loss of packet lost, we need to apply error correction techniques. Our target is to encode the ongoing packet in such a way that the k out of n received package is enough to reconstruct a k correct package. Now we have a basic form here. We have interleaved transmission and no interleaved transmission. And they say that if you go treat the effects of A is interleaved transmission. From the lessons from this very one, the interleave is that here is the sender, the delivered packet. The packets concern a set of data items, a sequence of data items, as we also mentioned that packets have data item which may be redirected or not. Here you have packet have about 4 data units. Now if we send this very one, this one first one arrived, this second one too arrived. The fourth one, the packet is lost, and the fifth one entered. If you are playing a video like that, for example, you are making audio call or anything that have to do with that, maybe a video, maybe you are playing a video too. Now that this packet is arriving like this, when this thing that you are going to have a gap that will jump to another step that you have to play. This very step here, they are not going to transfer. It's in re-communication. We're not talking about sending the data. When it's lost. We're not sending. Then there'll be a large gap here for transmission. Now, what if we disorganize it in a kind of, okay, in 1 second we disorganize the data, in 2 seconds we disorganize the data, instead of that being serial. Every 2 seconds we are sending data, but we are disorganizing it before sending. We are sending about 4 times in every 2 seconds. Maybe we are making an audio call. Okay, we send the first one, send the second one, send the third one, send the fifth one. Now, if we are reconstructing this thing, at the end of these 2 seconds, the receiver will start receiving. Okay, take it out. Okay, we receive. We were observing that there is a packet loss. After this, within 2 seconds, we are able to send this thing. The receiver will observe that, oh, there's a small deviation, but we'll be able to that the construction. It'd be good that we're getting that. Let us look at the lessons derived from this. Non-interleaving is equivalent to the best of efforts. That is this one. It's equivalent to that best of effort. The only thing that is different here is they group the data such that it will be sent in a packet. They explain it as in the packet. Meanwhile, let's go back to this. This one, this is packet 1, packet 2. But here they are explaining each individual packet now, which will have packets like that. And the non-interleaving transmission requires a small amount of different, hence startup is to be. This very one requires a small amount of buffer before it could start up. You don't need to send up to 4 times before you start the first transmission. You can start transmitting to that, and the startup is as compared to that interleaving. The interleaving is the last one. The no interleaving transmission will provide a large gap. It's providing a large gap as compared while the interleaving will display gap over the time, which is small. The gap is small, and the no interleaving transmission gap is solved by interleaving transmission. Meanwhile, it brings another thing that the buffer must be much, or the time the receiver will start receiving will be more. Okay, now stream synchronization, which is the last part of the the lesson. Synchronization deal with maintaining a temporal relationship between streams. We are sending these streams, we are sending them in packet, but we want them to be the temporal relation when we are sending and in a set of pictures at 1 second, so maybe 30 frames per second. We should send them 30 seconds. Those and the video, the audio that we have to send. That is our video is the images. Because the audio will have the corresponding audios. We have to send to it. It should be in line with it. But first of all, let's look at we have two types of synchronization that we call the simplest form is that between a discrete data stream and the audio and a continuous data stream, which I've explained here. The discrete stream, like the motion pictures, which will be discrete. The pictures are discrete, and the continuous, the audio file. The demanding type of synchronization is between a continuous data stream and a continuous another between two continuous data streams. Between continuous data streams, that is two of them. The two issues that we need to discuss the basic mechanism for transforming the two streams and the one if the distribution those streams is networked environment. Okay, at lowest level, the synchronization is done explicitly by the data unit of the simple streams. There's a process that can simply execute read and write operation on the several streams, ensuring that those to adhere to the specific timing constraint of the system. That is, there is in OS, you have something that can read and write any stream that is coming to application that is making request of it. You don't want to anything. Maybe if you are sending an audio, you can send two. You send your motion picture on one stream, the audio to in another stream. Then the application will be having, will have to manage it. The issue there is that the application will have to manage and will have a problem of taking the overall process. Like I've said, the drawback of this process is that the application is made completely responsible for implementing the synchronization while it has only a low-level facility available. The low level that if the operating system can giving that to an operating system is not good enough, because the system is the operating system can do that thing and just give them in one stream. It will be better. A better approach is to offer the application interface that allow more easily to control the stream device. With this control application, the developer can write a simple monitor program that consists of two handlers. For example, is a stream that jointly check if the video and the audio stream are sufficient. That is, they're sent up to a required standard to adjust the rate at which video and minutes are present. A typical multimedia middleware system that is here. The middleware is ever a collection of interfaces controlling audio and audio stream, including the interfaces that are used. That is how a multimedia middleware that is collecting this thing in our operating system. Then it's sending just one of it to this. Two of this thing is sending there. Each device stream has its own interface, including it. That everything is there. Lack of time. Let's move forward. Last one, the distribution of synchronization. But before I talk about, look at this thing. This very one is they are coming to, but the OS is the one managing when the data they synchronizing everything, just sending one particular something into the application. Now, if the first issue of synchronization is to build operating system by application to demanding for data, if the application can handle, if it's to handle, it becomes complex to write simple stream. You are writing two streams, it becomes complex to write them. The second issue is that if we're having complex streams, it should be done by the sender and at the receiver. That is, are we joining? Should we join this stream at the sender or at its receiver? We're not talking about distribution of synchronizing mechanism. When should we join these streams? Those are the questions. As it at the receiver, the basic one that shows that the two streams are coming to the receiver, and the receiver is the receiver OS is the one that is joining it. The first one was that the OS not even joining, it's passing it directly to the application. Application is managing. The thing become congested because of the transmission. And the other one is that is the receiver is not the one. The OS is the one joining it. The OS is the one joining the streams. And the third one is that if it's distributed here, can we have a better approach? The first issue is synchronizing to handle by the operating system or by the demanding operating system or the application that is demanding for the data. If the application is to handle it, becomes complex to write a simple stream. The second issue is having a complex stream. The stream should be done at the sender or at the receiver. That is it the sender should join the stream so that the synchronization will take place? Should we combine the data at the sender, or we should we separate them at the receiver at the end? And that is all about this stream communication. Goodbye. Have a nice day. Thank you.